Okay. Hello everyone. I will be presenting our work MSCG-Net models for the first agriculture vision challenge. This is joint work with Michael Kampfmeyer, Robert Jensen, and Amber Saarburg. So basically, the challenge is about developing novel and effective methods for thematic segmentation from aerial images. And the task is very challenging, mainly due to the heavily unbalanced labeling datasets with extreme annotation sparsity. The below figures and images illustrate some examples from the challenging dataset. So to address the challenges, we propose a novel model structure, namely a self-constructing graph model. The SCG model learns to create global context relationships by transforming a 2D feature map into a latent graph structure. Then the graph convolution network, GCM, is exploited to update the node features along the edges of the graph, and also to boost the model's accuracy and capability. We further extend the SCG model to multi-view SCG model by taking augmented input features and update fuse the multi-view representations with the rotation invariance. So we call it MSCG-Net. The details of our model architecture is shown as in the table and the figure. Generally, the proposed model consists of a convolution-based backbone layer, SCG module, which takes 3 view inputs and 2 layer GCNs, and the final fused output is projected and upsampled back to 2D domain for the final prediction. In order to tackle the imbalanced class issue, we also proposed a new loss function, namely adaptive class weighting loss, which basically makes use of a positive and negative class balanced function with the adaptive class weighting method. The design of adaptive class weighting is to iteratively compute weights from batch to batch according to the media frequency weight balance method. And also the design of positive and negative class balanced function allows the proper balancing of negative samples during the training process. And the tables shows the model size and the efficiency. So basically, our model is lightweighted. For example, the first model with the Sharath 50 as backbone, it has only 9.59 million parameters with 18.21 flops, gigaflops. And its inference time on GPU is very fast, achieves real-time capability. This slide shows the training details. We basically trained 3 models. The first model is MSCG-Net 50. We used the batch size of 10 images, but for the rest 2 bigger models, we reduced the batch size to 7 due to the GPU's limitation, because we train all our models with 1 GPU. And all these models take 4 channels, and the input size is full resolutions. And for the last two models, they are use the same architecture and backbone, but we use different training and validation images. And for other settings, like the optimizer and the learning rate schedule and the augmentation, we are all same. We didn't do any post-processing. So overall, all these models would take less than 8 hours to get the best checkpoints. So these two tables shows our final test results. The first table, we evaluated our single model with the single scale and single feed-forward inference. So generally, our single model achieves leading results compared with other single model with a single feed-forward inference. And if applying test time augmentation, it would give about 1% boost for each single model. And the second table shows model ensemble results with test time augmentation. So finally, our three model ensemble with TTA achieves the best mean ROU. So the total model size for the three model is about 71.57 million parameters. To sum up, in this work, we proposed a novel network architecture, namely MSCG-Net, where our single model achieved leading results with much fewer parameters and more computational efficiency. With the TDI and the model ensemble, our model gets further boost performance. Finally, our code and trained models are available at GitHub. You are welcome to check out, and we welcome any questions. Okay, thanks for your attention, and special thanks to the agriculture vision organizers.